All right, so here, after you've downloaded the Wolfram player at wolfram.com/player, you can find this simulation actually linked on the website. So you can go to the website. I'll show you the links afterwards in a second, but and you can play with this yourself. So this is really cool. So I'm going to notice I've actually set the frequency of the light to not be resonant right now, just so we can talk first. So I'm going to hit play on the light oscillations. And so notice the arrows moving back and forth, back and forth. Those are meant to represent the oscillations of the electric field of light, right? So here's our electric field of light. Imagine these are the arrows, right? So sometimes they're going in that direction, sometimes they're going in this direction. So the back and forth oscillation of the arrows is the oscillation of the electric field of light. Okay, what I'm going to do is I'm going to slow this down a little bit so that we can watch it in a little slower motion. So you'll notice, right, this back and forth, moving of the arrows, that is the oscillations of the electric field of light. Okay, so you'll notice then, that right now, that electron wave, it ain't changing, right? So here, the blue circle is meant to represent the edge of the sphere. It's not shaded in to save on some graphics power so that you can do this on your phones if you want it, or on your computers, right? Because the simulation is pretty computationally expensive. But the idea here is that this spherical wave, which we have a name for it, we're going to see, we call this wave 1S. You'll see why. You're going to do the pre-lecture videos. You'll know why it's called 1S. This 1S wave, because the light is not resonant, it's not changing. You'll notice a little bit of a jiggle. That's just because it's a negatively charged electron cloud. The light is electrically charged, right? It's an electric field. So there you go. It's a little bit of a movement, right? Light doesn't have any charges per se, but it is an electric field. All right, so that's when the light is not resonant. The frequency of the light is too low. So you're saying, well, let's pump up the frequency. Let's do it. I've now set the frequency of the light to be 4 times the natural frequency of the electron wave transformation. Now, ask yourself now, do you expect anything to happen? Remember, resonance. If you said that nothing's going to happen, you were absolutely right. Notice, look, it's still not moving. Still not moving. Why? Because it's not resonant. All right. And now, for the moment we've all been waiting for, we will set the frequency of the light to be the frequency of the electron wave. All right, ready for this? We're going to hit play. Now notice, as the light oscillates back and forth, because it's in resonance now, the electron wave starts to change. Are you saying like ooh and ah? I hope you're saying ooh and ah. You're not required to, but it helps. So again, just watch it. When it's not resonant, the electron wave stays a spherical wave. Nothing changes. But when it's resonant now, when we make the frequency of the light match a change in the frequency of the electron, now the electron starts oscillating in sync, resonance with the light, and it's moving, it's going back and forth. Now, this is not going to do 100,000 oscillations because that's a lot of oscillation. This happens a lot faster. But really, it actually takes 100,000 oscillations of the electric field of the light to make that transformation happen. And after those 100,000 oscillations, the electron wave has been transformed from what was called 1S to what now we call 2P. And this is a higher energy wave. The light has given some of its energy to this wave to make that transformation. All right, I want to point out a few things about this. So I'm going to switch screens for a second. So first, if you're looking to do this yourself, you can download the Wolfram player on Macs and PCs. It's free. I think it's not free on mobile devices, so don't waste your money on mobile devices, but download on your computers. It's amazing. And the simulation is on the website, on the handouts page. You can go to the website and download the simulation. All right, a few things I want us to take away from this simulation. First and foremost, you need to have resonance. If there's no resonance, nothing happens. If there's resonance, then there's a transformation from 1S to what we call 2P. But it takes time. It's not instantaneous. There's no jump, there's no leap, there's no instantaneous. It takes 100,000 oscillations of the electric field of the light. And so depending on what the frequency is, like we saw in class, if the frequency is 10 to the 15 hertz, it's going to take 1/10 of a nanosecond for that to happen, which doesn't sound like a long time, but is a long time for an electron. 100,000 oscillations it takes. But it costs energy, right? The electron wave is changing. Any change involves energy. So how much energy? It's called a photon of light energy. They're not things. Photons are not objects. If you go back to the simulation, tell me when you saw the photon, right? Yell, when did you see the photon? Don't yell. It's a trick question. There is no photon. There's no object. There's no photons here. All there is a transformation that happens, and that process has a cost. What's the cost of that transformation? The cost is a photon of light energy. It's an amount of energy. How much is a photon of light energy? Well, it actually depends on the frequency. It's Planck's constant times the frequency of the light. Or since you know that nu is c over lambda, it's also Planck's constant times the speed of light over the wavelength, right? And so this is a really, really important idea. And again, so here's a direct link to that CDF simulation, or you could find it on the website. I also wanted to point out that we looked at this this other. I tried to draw this, but I didn't do such a great job. And we said that this over here, these lines in the spectrum represent emission. So let's see what emission looks like, shall we? So let's go back to the simulation. So absorption was this direction. We started with a low energy electron wave, a 1s wave. And over the course of 100,000 oscillations of the electric field, the 1s wave became a 2p wave. That's absorption. The light loses energy and its amplitude decreases. Its frequency stays the same, but its amplitude decreases. And the electron wave changes from a 1-loop wave to a 2-loop wave. What's emission? Emission is the opposite direction. Emission is when the wave starts out as a high energy electron wave, and over the course of 100,000 oscillations, it's going to become a lower energy wave. It's going to go and it's going to transform itself from 2p to 1s, emitting the light. And so if you were to draw an energy diagram, and we're going to do a lot of these in class, if this lower energy state corresponds to the 1s state, and this higher energy state corresponds to a 2p state, well, absorption is the process of 1s becoming 2p. And this amount of energy is a photon of light energy. So what's emission? The opposite process. And we're going to be talking more about that in the coming lectures. And so to summarize, absorption is when light is absorbed by the matter, making it move. How much energy is exchanged? A photon of light energy, but only one atom, one electron, one absorption of one photon of light energy. How much is that? hc over lambda, or h times nu. The atom's electron cloud gains energy, the change in the atom. And notice, this is a big deal. We're going to keep coming back to this. It's a change in the energy of the atom. It's gaining 1 photon's worth of light energy. The light loses a photon of light energy. It decreases in energy. What does that mean, though? What happens to the light in this process? Well, the frequency wavelength, they don't change, right? It doesn't go from being a blue laser to being a yellow laser when some light is absorbed. What happens is it gets dimmer, its amplitude goes down. But the thing is, in chemistry, we don't really care, or at least in this part of chemistry, we don't care about the amplitude as long as the amplitude's not 0, because then there's no light. In analytical chemistry, which is a really cool class, you'll learn about measuring changes in light amplitude and how it's related to the amount of matter in the sample. And in fact, you're going to do a little Beer's Law lab in Chem 101 this semester as well. So you'll see a little bit about amplitude of light there. But for this conversation, which is one atom, and we don't care about what happens to the amplitude. What happens to the electron? It changes shape. And I want to be really clear about that. It didn't, right? If we go back to simulation, it didn't change locations. Still the same place. It didn't get hot. Remember, this is not an orbit, please, right? This is an actual fully filled in sphere here. It's just, to make the simulation faster. It's not filled in. And it transforms to this. This is not some sort of complex orbit. This is also a filled in dumbbell over here. And I want you to think about this. What happens? It doesn't get farther away from the nucleus. Look, the sphere is here. It's right there by the nucleus. It's right there. It changes shape, and we'll see soon it changes also size during that process. We're going to talk more about that in lecture. And finally, emission is just the opposite of everything we just said above on this slide. So please play around with that simulation. It's so uber super fun.